Welcome. My name is Jaime del Palacio, and I'm a software engineer on the Instagram virtual reality team. I'm very excited to be here today to talk to you about spatial media on the Instagram VR app. Over the next 20 minutes, I want to share with you the journey that we took to make Instagram a true VR experience, some of the challenges we faced, and the approaches we took to solve. First, I want you to imagine that you have a VR headset with you. Place it on your head and experience the clips that I'm about to show you. These are some of the ways you can experience Instagram and Quest headsets today. You can pin your IG experience to a wall in your virtual environment, for example, or you can experience it in mixed reality in your living room. As you noticed, all the content in IG feed is in 3D. But how did we get here? In early 2024, we set out to build a native Instagram app for the Quest headsets. We wanted to really supercharge the experience of social connections, and what better way to do it than through Instagram? By October 2024, we had launched our first version. This has the basic functionality, like home feed, reels, stories, your profile, but we wanted more. We wanted to be able to offer our users a true VR experience. We wanted to bring virtual reality to IG, and we wanted the IG content to become to life. Basically, we wanted to make a more immersive IG experience, amplify the user's social experience in VR, and give the users something that they can only view in VR. We wanted to offer all the content of IG in 3D. Stereoscopic images and videos would give us that VR-only experience. And we knew we could leverage AI to make this happen. But what does it take to build a stereoscopic image or video? Basically, a stereoscopic image is an image that creates the illusion of 3D. By presenting slightly different versions of the same image to the left eye and the right eye, we trick the brain into seeing depth. Basically, we shift pixels around based on the depth of the content. Remember the 3D movies with the blue and red glasses? It's the same principle. Creating a stereoscopic image is fairly simple. We take the original 2D image, we run it through an AI model to estimate the depth of each pixel. These models are called monocular depth estimation. This generates a depth map for each pixel that then we use to shift pixels around and to inpaint the missing parts. Finally, we encode both sides of the image into a single file. This is not a new concept. Stereoscopic, or spatial images as we call them, have been around for many years. And most recently, AI models have been used to estimate the depth of the objects. These have been used in 3D model reconstruction and autonomous cars, for example. There are currently many models in the market that vary in quality and performance, but most are not suitable for real-time applications. We needed a high-quality model that would work in real time, so we created MetaDepth model. But what does it take to make it work at IG scale? Just think about how much content and how many users use Instagram all over the world. That presents a real challenge. So we're going to talk about some of these challenges at IG scale, the latency requirements we faced, some of the quality considerations that we took, and finally, some learnings and things that we're working for the future. As you know, Instagram has a very big user base. Millions of pieces of content get uploaded to Instagram every day. All in different formats, different sizes, with different kinds of content. But only a very small subset of that media is ever displayed on Quest. And we wanted to make all the content that gets displayed on Quest in 3D for our users. So how do we make that happen? How do we make all the content of IG available in 3D for Quest users? Let's take a look at some of the decisions we had to make. The first decision was when to convert the media. We could do it at creation time, when the user creates a post. At that point, we would have more time to convert it. But the problem is we don't know which posts will be displayed on Quest at that point. The user simply uploads the image, and the system distributes the image across all the users that consumes it. So to achieve our vision of creating all the content in 3D for Quest, we would have to convert everything, all posts, into 3D. As you can imagine, that would take a lot of compute power at IG scale. But most importantly, most of those conversions would be wasted, since we would convert something that would never show up on Quest. The other option was to convert at consumption time, when the user watches the media on the app. That would guarantee that there is no wasted conversions, as would only convert what is actually displayed on Quest. We would need less power to convert because we don't have to convert all of the IG media, but it's highly sensitive to latency. Users usually spend a few seconds per post and are not willing to wait for minutes for a conversion. So the pipeline would need to be very, very fast. The second decision was where to convert. Again, we had two options in this case. First, we could convert it on the client or on the headset. In there, everything is local. There's no need to talk to the servers, there's no overhead, it can work offline. But it requires some amount of CPU and GPU to be available locally. And Quest is limited in the compute power. It's only a simple device. And the compute power needs to be shared across many apps and across the OS, and you could have many applications running at the same time. The other option was to do it on the server, taking advantage of caching for multiple users of one converted media. We would have more compute power for better quality and more flexibility on what we do, but it requires a fair amount of GPU capacity. In the end, we decided to make conversions at consumption time, when the user watches the media on Quest, and on the server, taking advantage of better quality and have more flexibility of what we could do. But we needed to make the conversions very, very fast. Which brings us to our next problem. Our initial benchmarks showed that we were taking around 200 seconds to convert a 20-second reel. That was too much. That could work for images, but not for videos. Users can't wait for 2+ minutes to wait for a video. So we needed to make it faster. Our first and naive approach was take a video, extract the frame, save it, tell the GPU to process the depth estimation for that frame, save the depth map for that frame, load it from the CPU and run the warping and inpainting algorithms, save the outcome, and then run this for all the frames in the video. Once all the frames were converted, then we would run the encoder and add them up into the final video file. As you can imagine, this was very slow. So what did we do to make it faster? How do we make it fast enough? Our target was to be able to convert a 20-second reel in less than 15 seconds. We took 3 strategies to optimize our pipeline. First, parallelization of the process. Then, a lot of code optimization and tuning. And finally, we wanted to get ahead of the user as much as possible to be ready to present the videos. To parallelize the work, we split the work into all available GPUs in one host. Each video is split in chunks of frames, and then each chunk is sent to a GPU to process depth estimation and post-processing. Then, once all the chunks are converted, we send it back to the CPU for progressively encoding the frames into the final MPEG file. Additionally to splitting the workload, This approach also helped in reducing the overhead of moving data from the CPU to the GPU and back. We also worked on many small code optimizations that yielded very big wins. For example, we quantized the model to a smaller floating point size that helped us make it faster without reducing quality. We also tested a lot of different chunk sizes and split ways. And finally, we tuned the encoder parameters to achieve the highest possible performance without compromising quality. We also needed to get ahead of the user, so we wanted to trigger the conversions as early as possible. As soon as we knew the post was going to be delivered to the user on the Quest headset, we triggered the conversion. That gave us around 2 seconds of lead time for the rest of the process. Also, from the application, we requested videos in batches, multiple videos at the same time. That would trigger the conversion of many videos, and we have them ready for user to play. We also tune batch sizes and timing to always be ahead of the user as this scrolls. All this work paid off. We are able now to convert faster than real time. Most of the videos are converted in less than 10 seconds. And this enables our vision to convert all content of IG into 3D for our Quest users. But what about quality? We took 3 different dimensions into consideration. First, comfort. Then, depth filling, or how much depthness we introduce into the image or video. And finally, quality of the resulting image or video. IG has many types of content. Users scroll through their feed, they jump from reels to home feed, they jump from another section, they watch their friends' stories. And we wanted to ensure that the users have a comfortable looking experience in 3D throughout all this time. We know that looking at 3D can be tiresome sometimes. It can cause nausea for some users, and we were worried that having multiple media scrolling at the same time in 3D would cause users discomfort. So we adopted a top quality principle. Do not make users feel discomfort. Comfort is related to the depth filling. When an object appears in front of the screen, we call that negative parallax. It is when the convergence point is in front of the projection plane. This gives for a very impressive 3D effect. Things jump at you out of the screen, and you can really feel the 3D. It has a very, very big wow factor. But it's also tiresome to look at for long periods of time. So we analyze other options. Zero parallax is when the convergence point is at the projection plane. It gives better comfort, but it still presents some problems, causing nausea, and has some window violation problems. Finally, positive parallax is when the convergence point is behind the projection plane. It's as if you're looking through a window into a 3D world. And although it has the least wow effect, it is the most comfortable to look at for long periods of time. So we decided for positive parallax. Another big problem for quality was text. IG posts have a lot of text. Posts tend to have stickers, they have text that is not part of the physical image. And this presents a big problem for depth estimation models. The model thinks that the text is part of the image and makes it follow the contour of the physical object, giving for a very unrealistic situation. So to fix this, we added a model to detect the text on a post and place that text in front of the rest of the images, the elements in the image. And that mostly fixed our text problem, giving a very natural feeling of where we place the text. To summarize, we developed a new depth estimation model. We took it from 2 minutes to 10 seconds. We integrated a pipeline that can handle all Quest traffic. And finally, we gave our users the immersive experience we were looking for. What are some of our learnings? First, a lot of the time in AI-related projects, you trade off latency, quality, and compute power requirements. In our case, we needed to find an alternative to the latency requirement and be very clever on when and how we do the conversions. Also, always optimize for the user. The comfort was our first concern. We traded off the wow factor for comfort. Finally, let's take a look at some of the challenges we're doing for the future. We want to make the IG experience even more immersive. We wanted to get to immersive to a point where you can walk into an environment, look around, and really experience what it was like to be in that post. And to make this a reality, of course, is going to need a lot more compute power, and everything needs to be faster. So we have our work cut out for us. I really appreciate your time, and if you're interested in this space, I would love to hear from you. Thank you.